Now let's look here for a moment, right here at the index of refraction for fused quartz. Notice it says that the index of refraction is 1.46. However, it's not exactly that for every single color of visible light. Here I have a plot that shows the index of refraction for fused quartz from 300 nanometers up to 800 nanometers, with the visible region being right in here. Now you'll notice there's a very definite curve here. I want to caution you. Notice this is only a very slight change here. This is 1.46, right there at a green wavelength. It gets up to 1.47 and down to about 1.55 at the limits of human visible light. So it's really only a very slight change. The reason it looks dramatic is that we've blown up this axis a lot so that we can see it. However, what this does mean is that we will get a slightly different angle of refraction for purple light and blue light than we do for red light. With a larger index of refraction, blue light will bend a little bit more than red and orange light. So as I bring that in here, you can see that when white light comes in, then as it refracts into the glass, the fused quartz, the blue bends a little bit more than the red does. In reality, the difference would not even be this dramatic. It's a pretty small difference, but it is there. If we were going from the glass back into the air, then again the blue is the one that bends more, which takes it further away from the normal. This is known as chromatic dispersion. Chromatic means color-based, and dispersion means separation. So it's just separating the colors of light. Now, what effects does that have? Well, sometimes we might take the light and shine it through a prism. This is just a piece of glass. We shine it near the maximum turn it can make, and as the light comes out, it separates into its different colors. And we see very pretty rainbows coming out from just white light that came in. White light comes in, the blue bends a little further from the normal than does the red. Then at the other side, the blue bends further away, giving us a more dramatic shift. In nature, you may have seen this if you've ever seen a rainbow. What's happening there is light comes in, it hits, the red light bends a little bit, the blue light bends a little bit more. It bounces across the bottom, and as it comes out, the red again bends a little bit, the blue bends a little bit more. Now, if you look just at one drop here, you might think, mistakenly, that the red would appear below the blue. But remember, you only see light coming into your eyes. So if the red gets into your eyes, this blue is just going to go totally over your head. In other words, if you're right here, the red beam reaches your eyes, the blue beam goes over your head. To see the blue, you have to look further down in the sky to a lower raindrop where that higher beam comes and actually hits you in the face. So you actually tilt to a lower angle to see the blue. As a result, you see the red on top and the blue on the bottom. Both of those are examples of chromatic dispersion, separating light because of a difference in index of refraction. One thing that Isaac Newton showed is that you can take this rainbow, put it back through a reversed prism, and turn it back into white light, which was how he showed that white light was in fact just made up of many different colors of light.